Hello everybody, today we will be talking about, we continue talking about shortest paths in the graph. Today we will understand the further algorithms for the same problem, find the shortest path from some vertex or find the shortest path between all pair of vertices. And probably at the end we will talk about their minimum spanning tree if we will have time. I think we will, but I'm not 100% sure. So can you tell me, what was the problem with Dijkstra algorithm? What was the main thing why Dijkstra worked? We discussed it the last time, but I want to mention this again. Do you remember?
Like, didn't work, or what? How exactly it worked?
No. Which assumption do we have on the directed graph so that Dijkstra work? So Dijkstra works, yeah. What assumption did we have on the graph? To be more precise about the weights of edges.
All edges should have weights, and even maybe they have to be different.
Not exactly.
I remember there were like zeros and ones, but I don't remember the fact that it should follow some rules.
Okay, I expected that. Konstantin, do you remember? Probably.
No.
Okay, so the main problem with Dijkstra algorithm is that all the weights should be positive. Otherwise, it will not work because of the lemma that we talked about, that we always can have the nearest minimum vertex. It doesn't work when there are negative edges. So what to do with the negative edges? With the negative edges, there is a Ford-Bellman algorithm. So it's very important to understand that Dijkstra doesn't work on negative edges. Like you can make it work, but if your graph has negative cycles, Dijkstra won't work. How Ford-Bellman algorithm will work? We will calculate the dynamic programming dki. The shortest distance to vertex I of path of length k. So this means we find the shortest path of length k that ends at vertex I. Yeah, of course let us suppose that the starting vertex is 0. Okay, can you tell me the base of this dynamic programming? D0. What will be in D0? Like what are the shortest paths from 0 vertex when you can move only 0 edges?
0.
What 0? There the length of this array is n. Like how this array looks like. The answer is simple, like as always. Simple and
Could you
stupid.
please read, because it's not clear. What is the shortest distance? I cannot recognize the text. The shortest distance.
Okay.
Vertex of path of length k.
The shortest path. Okay. Two vertex. So this is the shortest path of length k to vertex I. So what is the shortest path to 0 with the length 0? To the vertex 0 with the length 0. Okay, so it is 0. Like you start at the vertex 0 and the length of the path to vertex 0 is 0. Okay, that's reasonable. And everything else is plus infinity because there are no such paths. So what's happening? How to recalculate that? Suppose that we want to calculate dk plus 1 from dk. Do you have any ideas how to recalculate the next layer of the dynamic programming from the previous layer? These are the paths of length k, and these are the paths of length k plus 1. So what should we add to the path of length k to get the path of length k plus 1?
What should the length be? Or
No, we should add an edge. Okay? So we should add, like, these are the paths of length k, and to get the path of length k plus 1, we should add one edge to the end, right?
Right.
Okay, so do you have any ideas how to recalculate the dynamic programming of k plus 1 using the dk?
Do we know vertexes for this k, for this path, or not?
No, we don't know. We just now we simply maintain their shortest distance, the shortest path. So we like the length of the shortest path.
wouldn't it be just like 1, infinity, 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 and etc.?
So for 0 it is 0, infinity, infinity, infinity. But like okay, let me.
Maybe we should for every vertex I, we should find the nearest vertex and add the distance between these two to dki.
Yeah, exactly. So what is your path looks like? So you get to the, like, there is length k, and you have the vertex, yeah, that for me it will be v. And then we add the vertex u to that. So you go over each edge that go out of v and update the distance for u. So you know that the length of the distance k plus 1 to u will be the distance to v plus the distance to this edge, the length of this edge. And you have to calculate the minimum of such paths. So the recalculation will be simple for V, for all the vertices, for Vu d of k plus 1 u equals minimum of dk plus 1 u e dk of V plus weight of UV, of VU, sorry. Okay? So you simply go over each edge and try to relax the best path of length 1 bigger. Okay, can you tell me how many iterations should we do of this relaxation? So this is the relaxation. So how many times should we do relax?
When we go from k to k plus 1?
No, yes, when you go from k to k plus 1. So what is the maximal k should be?
The maximum k is the sum of all edges of the graph.
Okay, let me straight this in another way. So, suppose you know that there is a shortest path from start vertex to some vertex V. Okay? What is the number of edges at this path? What can be the maximum number of edges at this path?
Number of vertices minus 1.
Yes, number of vertices minus 1. That's a good start. So, what k should be the what maximum k we care about?
Could you please rephrase the question?
Okay, the question is, we calculated an int programming so that dki is the shortest path of length k, okay? We know that each shortest path has at most n minus 1 edges. So how many times should we perform this relaxation for a different case? So k is from 0 to
n minus 1.
Yeah, to n minus 1, yeah. That's it.
We should perform the section n minus 2 times.
Yes, we should perform this section n minus 2 times for duration 0 k minus 2. Oh, to n minus 2. Yes, exactly. But this almost works. There is one problem with that. Suppose you have a graph with negative edges. Can you give me an example of the graph so that there are vertices with no shortest distance? So this means that distance can be as small as possible. Okay, let me skip this. The problem are the negative cycles.
You mean like if we have only one vertex or what?
No, negative cycle, this means that, for example, this is 1, this is 2, this is 3, this is minus 10, this is 3 also, I don't know, like, and 1 out. The problem that this vertex doesn't have the shortest path to it. Because we can go to the cycle and go over a cycle many times. And then we go to the end vertex. So it doesn't have shortest path simply. Because this path, like, there exists a path with as small as possible. So we can put any threshold and we can find a path that has a length less than this threshold. Okay. By the way, please tell me how to get the answer to the problem from this. So we calculated dki. So how to find the shortest path to I? Where the answer will be.
Shortest path to I from start, from 0, right?
From 0, yeah. This is dki is the shortest path of length k. So how to find the shortest path to I?
It should be shortest path to actually, it's not clear for me. The shortest path, it means to vertex I. It means the shortest path from some 0 point.
From the start. Yeah, from the start. From start.
Okay. And we have to calculate the shortest path to
all vertices from the start vertex.
Mm-hmm.
Okay, so let me open then the chest, the treasure chest. We should iterate over all k.
We should iterate and compare it with, let's say, some neighbor vertex and then path plus edge between these vertices.
No, this is the relaxation part.
Right.
I want to get the answer to the problem. The shortest distance will be the shortest path for all k's. So for I, you fix I, you traverse over all k's, and you get your answer. So the minimum out of all these cases are the answer. Okay, so like let me paraphrase the problem a little bit. So let us say that the shortest path of length less than equal to k. Then we should say here that d of k plus 1 equals to dk. And everything will be the same, except that now the answer will lie in dn minus 1i. If you just change like less than equal to k and copy the array from k to k plus 1 before, then the answer will be in D n minus 1 I. So, sorry, like that's a little bit different. I will explain how to write this algorithm like in a little bit different manner, but I will build it step by step. Okay, so now we have the negative cycle. What to do with that? So now we want to find the shortest path to the vertex that have shortest paths, and for all other vertices we want to say like no, there is no shortest path to it. Like this means that there exists a very small path there. Okay. So the thing is the following. So like, let us calculate like the last D, where D was dki is shortest path of length less than equal to k. Less than equal to k from start to I. So we already calculated D n minus 1. So this is where the answers are. So D n minus 1I is the answer to our problem. So how to find whether we have the negative cycle? It appears that if you apply the relaxation one more time, dni, one more time, and there is a vertex for which d n w not equals to d n minus 1 w, this means that w belongs to negative cycle. So let us see for this example. So we start from 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We started from 0, infinity, 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 infinity. Then we copy from the previous array. We found 0. Then and add one relaxation to 2. 1, infinity, 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 infinity. Then we relax one more time. Then we add from, like we copy from this one and relax one more time. So it is 0, 1. From 2 we can relax to 6, so it is 2. And from 2 relax to 3, it is 3. Infinity, infinity. Then we relax from 3 to 4. And finally we relax from 4 to 5. How much minus 5? So how many we have? How many vertices we have? We have 6 vertices, and we do 0, 1, 2, 3, 4. It came faster than I did, but like on the 5th, it will be here. It will be uh, 0. 2 will be updated. So 2 will be updated with it has in 5 it has -5 and updated -2 to 2, and everything else rests the same. Then we update all other vertices and we update from 2 again. So it will be 0 -2. From 2 we relax to 6, it will be -1, and to 3 it will be 0. And so on. This can go to infinity. Like you can update this cycle infinity. So this is n-1, and this is n. You can see that between n-1 and n, we have 2 vertices with a different. Okay. Not W belongs to negative cycle. Not right. For each cycle, negative cycle exists W, so a little bit different. So we have updated for 6 and 3, and 3 will be on negative cycle. So this is the negative cycle. Or the W here, W is connected to negative cycle. So, how to find whether their vertex doesn't have the shortest path? So we simply run one more iteration and take all the vertices for which the distances are not equal. This means that this vertex is reachable from the negative cycle. But for each negative cycle, there will exist this W. Thus, to solve the problem, we just simply take this vertices, so here is 2 and 3 and 6, and we run their DFS from that depth first search. So we want to find all the vertices that are reachable from these W's. This will be exactly the vertices for which there is no shortest cycle. There is a small question how to get the shortest cycle. This can be done in a similar dynamic programming manner. You just maintain for each element D and W from which vertex you got the shortest path. Like as we did in the dynamic programming algorithms, we just store from where we come. And then, for example, if we get such vertex W, we just can go by their edges back until we cycle it up. So for example, for 6 is negative, and to 6 we come from 2. When we updated 2, we come from 5. 5 was updated through 4, 4 was updated through 3, and 3 was updated through 2. And we found this negative cycle there. So that is how you find the negative cycle, and you find the vertices that doesn't have shortest paths. Using Ford-Bellman algorithm. Like, other questions up to this point?
Well, I did have one, and I think it's kind of a stupid question, but why can't we just check if it is negative or positive number of length, like the weight?
Okay, so suppose that instead of -10, you would have here -3, okay? You would say, there is a negative cycle because I see the negative edge. But the problem is that when you update, so your update will be here, like the 5 will be 3. Like when updated from here. So it was 4 was 5. Okay, I did a mistake somewhere. Okay, never mind. Yeah, I did the small change here because it is 6, it should be 6 here. So everything that I wrote is shifted by 1, unfortunately. Okay, you can change it whether you want. So then 5 will be 3 to there. Then you will have 3 here. But unfortunately now 2, if you get from 5, you will get 6. So the 5, there is 5 is 3. And you will have 6, which is bigger than 1. And you can see that nothing has changed between 4 and 5. And never will change, like, at any moment after. So this is an example of the graph. You don't have the negative cycle. And thus, all vertices have shortest paths. Did I answer your question?
Yeah, I think.
Okay. So let me write the algorithm, how it is written typically. So it appears that you don't have to calculate it as a dynamic programming. You just can calculate di, shortest path of length at least less than, like, that's quite complicated, but I will like write the code and everything will go into the place. So now we maintain only di. So we have while true, relax equals to false. Then for all v from v and for all ages vu, we ask if d of u we just relax. We say that d of u equals mean d of u and d of v plus weight vu. No, I was writing if correctly. If we have to set this relax Boolean variable that we successfully relaxed. If du bigger than dv plus w vu, we set relax equals to true, and du equals dv plus w vu. And if not relax, break. Let me add here while iteration less than n minus 1. So we just forget about one dimension of our dynamic programming, and we just calculate for each vertex the shortest path. Previously, in dynamic programming, we have shortest path of length less than or equal to k. Right now, it can update more than k at the same time. That is why we have the relaxation, like the number of relaxation will be less than in the previous algorithm, because sometimes, for example, if you're lucky enough and you have the graph something like that, you will be done in one relaxation. So you, like in the previous algorithm, it was relax from 0, relax from 1, like relax from, okay, yeah. So like there is a right order kinda and no order. So there in the right order, when you have like you relax from 0, then 1 has updated weight. Then you relax 1, 2 has updated weight. Then you relax 2, then you relax 3, and you get the answer for all the vertices there. However, if you're unlucky and your graph looks like that, 4, 3, 2, 1, yeah, you can have, oh, sorry, like there, the edges should be in a different direction. We'll try to update 4, nothing happens. Update through 3, nothing happens. Update 2, nothing happens. Update 1, we updated 2 by that. Then we try to update from 4, from 3, from 2, and we updated the 3, and so on. So sometimes it is faster, and sometimes it is as usual. Okay. Can you tell me the worst complexity of this algorithm? So let us talk. Like, if it is not clear from the beginning, let us talk. How many iterations do we have?
It's n-1, and we shall go through all of the vertices.
So this is often, like the number of this calls is often. How many do we spend here? We already had this approach where we iterated over our vertices, and then we iterated over the edges that coming out of the vertex. What will be the complexity of this part? we did it several times. We already saw such loops where you iterate over all the vertices and you iterate over all the edges out of there. Okay, how many times, like, consider a separate edge. How many times we relax over this edge inside this loop, inside the outer loop? This is relax.
Or at least one, I guess. And wasn't it like the cubic thing?
At least one or exactly once.
Exactly one.
Exactly once. So what then the complexity of this will be?
It would be the number of edges.
Yes, exactly. So it will be the number of edges.
So the upper thing would be the number of vertices, so it would be like the product of all of those.
Exactly. So it will be the number of vertices times the number of edges. So this will be the complexity of the algorithm. I know it is not very good, however, it can work with negative edges, which is already good for us. So this is the whole algorithm, so nothing very hard about that. Any questions about Ford-Bellman algorithm?
No, not yet.
Okay, good. Okay, then we will come. So these problems that we mentioned right now for Dijkstra, for Ford-Bellman, for Bradford search, these were the single source shortest paths. So we find the distance from one vertex. However, sometimes we want to find the distances between all pairs of vertices at the same time. There comes Floyd algorithm. This algorithm is pretty simple to write, but it is not very simple to prove. So I will try to give you an intuition, but if I fail, sorry. I'm very sorry. Okay. So we are given an adjacency matrix A ij, and we want to calculate d ij. I will write the code right now, and then I will try to explain why this works and why this happens. At first we copy aij to d. So this is the whole algorithm. So you have the outer loop by k, then you have the inner loop of I and inner loop of j, and then you calculate dij, like of the two inner loops. This is very important, that k is coming over the outer loop, otherwise this will not work. So please pay the attention that the order of the cycles are not trivial as usual. Then dij, and we try to make dik plus dkj be compared. The question that you probably want to ask, why k is in the outer loop? Because as we thought, with different dynamic algorithms previously, for example, when we had ij, we split it in the middle and we iterated over ij and then k. Their idea is the following. At each step, this will be step. After that step means that dig is the shortest distance, between I and j, so that all the vertices in between, shortest path, distance path, all vertices with all vertices less than k. What does it mean? It means that, between I and j, we consider on the path only vertices that are less than or equal than k. So kind of we add one vertex at one vertex per time. So at the beginning we have separate vertices, then we take the vertex k and we go over all its inside and outside edges. So, and we just we know here dik the shortest path between I and k, so all the middle vertices are less than k minus 1, less than equal to k minus 1. Here also less than equal to k minus 1. And we kind of find the split where we add this new vertex there, this vertex k. So consider from the back. Suppose the maximal identifier of their vertex on the path is m, or I don't know, z. Then you have updated your, so this is I, z, j. So your path between dij is path between diz plus dzj. And z is the maximal identifier on the path. Okay? Is it clear why this algorithm works?
Just a second, please.
Sure. I'm waiting.
So basically, in simple words, it would be just like ij is I to k and k to j, right?
Yes, exactly. Yes, I to k and k to j, where the k is their maximal identifier, the vertex on the path.
Okay.
Okay, are there any other questions?
No, not yet.
Okay, you're thinking right now, right?
No, I think it's kind of clear now.
Okay, good. So, the question, how can we find where there exists a negative cycle in the graph? It is pretty simple. You just have to
Can you just like make it again and see if like the numbers changed?
Okay, that's one way to do this. True. This is one way to do this. But there is a simpler, like a little bit simpler way. Given this, like you just run once. I will give you a little hint that there we should initialize dii as 0. So, any ideas?
Just 30 seconds.
Okay, sure.
wouldn't we get like a negative result on in the process? Just like, okay, I think I don't know.
Sure, you don't know. I gave you a huge hint. Huge hint. Like enormous, of enormous size. Okay, let us thinking a little bit other way. So suppose you have a vertex V on the cycle. What is the cycle in the terms of path? It is from which vertex to which vertex?
I didn't get the question.
So, see that we have here like the distance from vertex I to vertex J, okay? So consider the cycle. Cycle, it is the vertex V on cycle. So the path is from U to V. Then the cycle is what? It is from V to
V.
To V.
This is the path. You mean that?
Yeah, kind of. If you have the negative cycle, your dii will be negative.
Yeah, it was very close to the answer I had in my head. Like, we'll get the negative result. Yeah.
Yeah, it is almost, yeah, but you have to apply one more step, like one more relaxation of there. But right here we simply compare dii or dvv with 0. And if it is less than 0, then this is the shortest path. Okay. Another interesting question, though, which you should answer: what should I do if I want to restore a path? So I want to get not only the distance between two vertices, the shortest distance between two vertices, but also I want to restore a shortest path. So I want to know all the vertices that are in that path. How to update this? What should we store in order to get this information out of this algorithm?
Can we just use a queue to store like the start and end point of each edge? And then to find an answer, we would just find like the first and last numbers.
Can you repeat, please?
Like, cannot we just use like Q to store the information of this short, like?
Okay. Let us then. I ask a different question. What is the complexity of this algorithm? You should be able to do this in no time. Like, if you do not answer, then I did everything wrong.
Oh, I'm sorry, I thought that we should do this algorithm in null time, and I was a little confused.
No. The complexity of this algorithm.
Well, with this step for n-1 times, like this step that...
Which is?
It is written like in the squared brackets.
No, which is? Like how I typically, I do not have any -1s in the complexity. What will be the complexity?
So it is n, just n.
Just n in?
Just a sec. Is it cube? Like
yes, it is.
3?
It is all of n cubic. Because we have 3 cycles, and each of them is of length n. By the way, please note that this is from 0 to n minus 1, so the length of the cycle is n. Okay, what is the memory complexity of this algorithm? So how many memory does this algorithm use? How much? Sorry.
Is it n?
M?
Oh, okay, n, yeah.
No, we want to calculate from each pair to each pair. What are the sizes of D?
So what we store is some kind of a matrix, and it is n to m, like nm.
Not an m, n times m it is.
Okay.
From the vertex to the vertex.
Oh yeah, sure.
Okay, so what is the complexity then? Memory?
N squared.
Yeah, n squared. Like nothing hard is here. So yes, we have the dimension of the array n times n, and then the memory complexity is n squared. However, when you want to store the q per each thing, then you will have what complexity approximately? Memory complexity.
Well, it is n squared, and the q is just like n.
Yeah, so
n squared plus n.
not plus.
Yeah, we use it in the direction, so n q.
Yeah, it will be n cube. This is much higher than n squared, right? Can you do the restoring of the path in n squared memory complexity? So I agree with you that you can use q to add this. Okay, but this will have memory complexity of n cubic. Can you do this in of n squared memory complexity?
Okay, maybe like if we know the path and we know like the length, we can just make an extraction like minus the. I know, just a second. I need to think.
So you should think about the standard dynamic programming algorithm. You want to restore, like, you want to know from which state you come. And that's it. You should know from which state you come. And your state is from this case, like I, K, K, J. Like I will give you 3 more minutes and then I will explain if you don't come to the algorithm itself.
Okay, is it something with like distraction, like the minus operation?
No.
No, it's not. Okay.
Okay, let me explain that. I will give you an intuition, you will wait if you need them. So, as in standard dynamic programming approach, we should store from which state do we come to this. So, simply for, like, you just compare here, if dij less than d, this one, I set, bigger, sorry, bigger, dij equals to dik plus dkj, and then you store that for the ij we split by k. The last time when we updated dij, we split it by k. Thus, we have to simply recursively call for ik, then k, like, until we get answer for ik and k and get kj. That's all. That's the standard dynamic programming trick. You just store from where you come, from which state you come, and try to restore, like going backwards, to recover all the states. Oh, sorry, like not k. Yeah, it should be here. Pij and Pij and get, okay, get. And get something. Okay? Do you get the idea?
Yes. Not exactly.
Not exactly.
But I will Google it later.
We just store for, like, you want to understand how did you come to the best answer as you have. Your best answer was updated through the vertex k. Thus you have this vertex k on your path. Thus you store that for ij you passed through k. This was the maximum node that was on the path. Then how their path looks like. It is the path from I to Pij, then Pij itself, and then the path from Pij to J. Does it become clear?
Well, I understand why we get like from I to P, Ij, etc., etc. I just need more time on understanding what get and how it connects with dynamic programming thing.
In dynamic programming, we kind of store, like, it is kind of the standard thing to store the way how we get to the answer. Like, I don't know. For the grasshopper, we had grasshopper that hops somewhere. We store. From which part did you restore the dynamic programming? It was like from there, I don't know, from the position X, you went there from position X minus 2. And so on. So like, it is exactly the same as dynamic programming, because this is the dynamic programming, really. It is named as like finding the shortest paths, but it is dynamic programming.
Oh, okay, yeah.
Okay, do you have any questions?
Not yet.
Okay, great. See you then.